Okay, well, I guess let's go ahead and get started here. Make sure I'm recording here. Yeah. Okay. Well, so I was planning on, I haven't quite gotten back the assignment threes for everybody, so, although I got, I don't know, quite a few of them back, but not everybody. But I thought I'd start with that, a little bit of a review of assignment three. There's a couple of things that I wanted to discuss on that. And then there's a few more things we can talk about for logistic regression. So, so just to remind people that are watching this, I'll probably for this assignment three, I'll maybe try and post the example solution. So this one definitely would be useful. Although most everybody I've looked through so far was doing well on it. I didn't have anybody that seemed too lost, but still there's some interesting things that are illustrated in the assignment three. So I'll try to post an example solution here that I'm going to go over. And then we'll talk about maybe a few more things on logistic regression, maybe a bit of a light day today. Just as a reminder then, next week we are doing a review for the class, so we are going to have a midterm. So I'll start talking about that mostly probably on Tuesday next week, the format and stuff like that, in case people have questions about the midterm test and what to review for and those kinds of issues. So I'll try not to spend too much time on this, but I did want to mention a couple of things on the assignment three, at least at one point in the course. So when I post this, if you're interested, it does show you the parameters that were actually used for the function. So as a lot of people found out for the very last task, if you do a grid search where you're determining the best polynomial, so the best degree to use for the function that you fit, you'll find that 6 ends up being the best polynomial degree, which is actually correct. So it was a 6-degree polynomial that we're using. Those were the right here were the parameters for the values. You can, if you're also, you might want to go back and look at your best attempts at doing the ridge and the lasso. So especially doing the L1 that drives all the parameters to 0 except the ones that are useful. Although this function is complicated enough, you'll probably find that even your best regularization, you wouldn't have been able to get a real good. You wouldn't get all that close to what these parameters were. But you can go back and compare kind of what you came up with on like the 5 and 6 when you were doing some regularization. So and also once I post this example solution, so another point about this, another reason why it's good to maybe go back and think about this example is that normally when you do data analytics projects, when you're doing machine learning and trying to model a set of data, there's no reality behind it, or there's something that's really generating the data, but you won't ever really know what the true function is that generates that data, right? So a practice like this, where there actually is a reality that you can know, that you don't know what it is when you're trying to understand and figure things out, but you can go back after the fact and kind of compare what you came up with to what was actually true about the data. It can be very useful for you understanding and building your skill. That's another reason why doing like competitions, like Kaggle competitions and things, can be also very helpful for building up skills in machine learning and data analytics, because again, those kinds of data sets, there's often the people that publish them for the competition or whatever, they know what the reality is. So you have to do your best to try and model and get a good model that fits for the data. But after the fact, you can go back and see where your thinking was correct and where you were kind of off on stuff. So anyway, I do encourage you. Well, I'll post this as soon as I get all the rest of the assignment 3s returned. So I've still got a few more to do. I'll try to get them all back today here. Another thing that this assignment was meant to illustrate was some of the basics of fitting a regression in this case. So I often bring up, I didn't do it before we did this assignment, but when I'm talking about regression, it's common to bring up this example. You may have seen it before, Anscombe's quartet. So the point of this is for, like, if you're fitting a simple linear regression, the summary statistics that you get, for example, like the R squared and others, don't necessarily tell you. So the descriptive statistics don't necessarily tell you everything you really need to know. So it's important to, for example, to actually visualize your data as well to see what you're working with. So the point of this, if you've never seen this example before, is that the summary statistics, like the mean of these data sets and the variance of these data sets that we're fitting a line to, that we're doing a linear regression on, are actually all the same. And the R squared score of the fitted line is actually all the same. But it's obvious that the linear regression, fitting a line to this data makes sense in some of these cases, but it doesn't make sense in the others, right? So this is typical. So some data probably with some noise on it. So this is probably a good use of a linear model. It looks typically linear. The same with this one. This is really some linear data, but this is illustrating, this point is probably some kind of a mistake or an outlier. Right? So that outlier actually pulls off. You would get a better result if you would do some regularization. So another thing that regularization does is it fights overfitting. So in this case, it fights fitting to noise in the data. So that was another one of the points that this assignment 3 was supposed to be doing. So here, if you use what's known as a robust linear regression, which is it's similar to doing what we did with regularization. So using a linear regression, but you say that I don't want to minimize my cost function at all costs. We want to also take into account other factors, right? So adding some regularization to this, you would get an actual better fit on this line here by ignoring the noise there, right? So again, for a real data set, you don't know which points are outliers or mistakes, right? But by doing some different things, you can sometimes determine that these points are maybe not useful statistically. There might have been something wrong with their collection, or you can just use modeling methods that will strike a balance. We'll try and give fits that don't fit too much to the noise in the data, or especially things like this, outliers or mistakes in the data. And another thing, right? So this is another point of our assignment 3 was when you're fitting a model, you have to know something about the data set that you're fitting things to. So this one in the Anscombe's quadrant, even though you get the same line and it has the same statistical properties as this data set, is obviously a nonlinear relationship. So it definitely, you're not going to get good results trying to shoehorn a linear model on this. So if you use something more powerful, probably a quadratic, it looks like a squared model or something like that, you'll do much better. I mean, not only on the fit, but also at predicting unseen data. So. Anyway, so some of that stuff was also kind of the purpose of this assignment. So, and yeah, I usually do show that at least at some point in the course and discuss Anscombe's quadrant. So, and I'll just reiterate some of the points that were trying to be made on these. You know, so for you first we're supposed to create an underfit model. You know, I was expecting that if you, I mean, you know, if you did it exactly, if you did it correctly, if you did it the way it was described, you should have gotten exactly these coefficients. So I was usually double checking. So for the underfit model, you should have gotten like a 0.31 on the overall cost function when you look at the this is going to be the root mean squared error in this case with respect to my predictions on the data that we fit the model with. Okay, so we're using the same data that we fit the model with to make predictions with. So that's the root mean squared error on the training data in this case, right? So an underfit model, if you fit something, you know that it's definitely not powerful enough for the data set that you're trying to model. You still get some information from that. So that gives you kind of an upper bound, or it gives you a baseline case. So you know that, I mean, you know, if you get something that's going to get worse performance in terms of your cost function, or if it gets about the same performance on unseen data, on test or validation data, it's your model isn't really doing anything. So you should be able to do something that improves on the you know, this is kind of like an upper bound then of what you would expect a model to be able to do on predicting data that it wasn't trained with. Yeah. So, I mean, I had quite a few people, well, I had at least 3 or 4 people run into this. It's not really an issue with the way that people were implementing it, but the test, we're expecting that the seed, that a particular random number seed was generated because the tests that were run on this, and I do this for a lot of assignments, so I'll try and be clear on this when we do it, but so the test generates some data at random, but in order to get exactly the same results on what you pass in and what's tested when we test it using the unit test, we have to have the seed set to the exact same value so we get the same sequence of random numbers. So so some people that were setting the seed inside of their learning curve errors would find that it wouldn't pass the tests. And I didn't take much off for that. And anybody that asked me, I told them just to remove that seed there. So usually if you don't change the seed inside of your function, or when you do the train test split, there's also a parameter you can set, you can specify to set your random seed. So if you don't use those inside of the function, you just assume that the seed is set beforehand. You should get it to pass the unit test that we had in there. So I need to make that a little bit clearer in future assignments. But yeah, I had at least one person hadn't asked me about that and still had that in there. And basically, you can get pretty much everything to pass. You'll just end up failing like the 2 tests where it tests the first 5 results from your train errors and your test errors if you reset the seed inside of your function there. So anyway, if you ran into that is just something that we'll probably do the same thing in future assignments, so keep that in mind. So often when I'm testing, I need to generate just some random data will help me make a good test, but I want to be able to reproduce those things. So to reproduce it, we have to set a seed before we generate random data and test your stuff with it. So, Another thing, I mean, I said this for quite a few people, but when you plot these learning curves, I mean, you can get some of this information just, directly from displaying, so I know that the final root mean squared error was 0.31 for my underfit model, right? But, whenever you're creating a plot or a visualization, you should think about what it is, what message you're trying to convey, right? So every figure should be telling a story, right? So if you do these plots here, often if you don't constrain your y-axis, really the plot isn't useful. So let's rerun all these, run everything above this here. So in this case, the usual thing is that the range of the error on the data that you test it with will be really big in some points, right? So if you don't constrain the axis, basically things are splashed out here. This doesn't really give you any information or much information about what the relationship is between the train and test. You can't really see. I mean, you can kind of see on this one because it wasn't too big. It only went up to 14 instead of some really large value. But so what you're trying to see on these learning curves is like how long it takes to converge, and another important thing is the level that it converges at. So especially for the overfit and the underfit model, those aren't going to be good models, but where the train especially levels out at, so where your errors on the data that you train with levels out with gives you some information. Right? So again, it leveled out around 0.31 on the overfit model. So that gives you kind of a number bound on this one. But and also it is converging, right? So if you don't know if the model is underfitting or overfitting, you have to make a determination using something like this of whether it actually converged or not. And that's not always straightforward. I mean, this one did. I mean, they actually not only converge, they actually cross. Sometimes, though, it's a bit of a judgment call. I mean, is it converging if they, because it always depends on what the problem is that you're trying to fit to, what. And I don't know. I can't give exact. You can't give an exact rule on that. It takes a little bit of experience doing a lot of these to say, well, that's converging, that's not converging. Right? But that's some other information when you're plotting learning curves like this, or plotting the epochs of doing something like a gradient descent of, are my train and test errors far apart, so they still aren't getting the same results, or if they come together, converge at some point or not. So here we'll notice that for the underfit function, you were fitting a quadratic, just a power 2. So if you knew what the true secret function was, you could. So this is another reason why you might want to come back and look at the example solution. So the model that you end up coming up with and fitting, you could actually then visualize how it actually performed with respect to the actual function that was being used to generate the noisy data. So the underfit model will give you something like that. It's just a quadratic. So there's lots of places where it's going to not be able to estimate well. This is the best you can do with a power 2 model. In terms of reducing your error here. Right? So the purpose of the overfit model, let me go a little bit faster for the rest of these, but the overfit model does give you some useful information. So an overfit model should never really converge here. So, and again here, I probably didn't even limit this enough. I limited it like this just to show that, yeah, in fact, I mean, the error on the data that we're testing with is really big. And you can't really see it after the first, after training with more than 4 or 5 points on the data set that we have in here. So if we don't limit the axes here, all you'll see is that, because the error went up to above 1 million, 1 e to the 6, 10 million at some points there, right? So again, though, the point on this, and maybe we should limit it even more, because what we really want to know. So here, if you go down to 0.5, you can't see the test error at all. So even at the when it was the lowest, it was above 0.5 here. So, but what I really want to know, I mean, I already know that it's not converging. Right? So another reason why not limiting this, it's a little bit tough to tell whether it's not converging or not. Right? So if you just look at that, I mean, did it converge there? So usually the thing is it was really far apart, even though, if it looks close here, because it all got squashed down, it was still really far apart over here as well. Right? So it didn't really ever actually converge for the overfit model. But another thing that's supposed to be, if you are overfitting a model, another bit of useful information. So it's a signal if it doesn't converge that you're overfitting, because so I can get my data fit well on the data I trained with, but it just the performance falls apart when you evaluate it on data it wasn't trained with. Right? But that's characteristic of an overfit model. Right? So, if it's not converging, it's probably overfitting. The other useful bit of information, though, is that this gives you a lower bound, right? So, if I get a really good model that's just right, not overfitting, not underfitting, you probably can't get exactly down to as low as what you'll get on the overfit model on the data it was trained with, but that's kind of a goal. That gives you a lower bound. So I should be able to try and build a regression model that approaches, about 0.25, 0.3 or so, 0.025, 0.03 for my root mean squared error. Right? So I know if I can get a model that's not overfitting and is approaching that on the validation of the test data, that it's probably a good model. All right. So here, again, this is classic, trying to illustrate that this is overfitting. So this was supposed to be, you were supposed to do a degree 100 polynomial, and this is typical of this kind of thing. So it'll be really wiggly, especially on the ends of the range here. That's because the higher powers allow you to really just go wherever you want to. Especially on the endpoints of stuff, so it kind of goes around. But those are especially those areas are the ones also that really tank the performance on the held back test data. So it'll do really poorly. It'll predict really wild values out here that will be far away from data it wasn't trained with. It's not exactly going through the point. Okay, and for the rest of these, I was for the ones I've looked at so far, I was pretty happy with the work on the doing the lasso. So yeah, for the first one, the lasso regression, I always kind of forget, but this will be the one that will typically drive things to 0. So this can kind of give you an estimate of, in this problem that we're working on of what the degree of the polynomial might be, although, again, it was probably going to be tough to get really close from this, but you can probably tell it's around 10 or something, at least if you were doing as was described here. So the goal on here, if you're doing this by hand, would be to try and find an alpha that's obviously still overfitting, an alpha that's still obviously underfitting, and then something in between that gets a good root mean squared error, a good cost that's hopefully approaching that 0.025, 0.03 or so, as close as you can get it. In this example, actually, I can't remember. We'll look at the table here, but this was a alpha of. So yeah, for us, and we obviously get much better than the underfit model. So the underfit model was about 0.3, but even some of the best alpha that you can get here. Probably you would only be able to approach about 0.1 instead of the 0.03, 0.025 I was talking about. So here we're coming in somewhere around about 0.12 with this. So it looked like it kept about the first 1, 2, 3, 4, 5, 6, the first 20 or so parameters. It had something, some value for the first 20, and got everything bigger than that pushed down to 0. And again, we can get, so we can look at what it does with the lasso, with the actual true secret function if we want to. For me, in this problem, even though the ridge doesn't push the things down to 0, you can get much better results. So I was usually getting much better results. It was easier to find, a alpha on this one. So in fact, like this one that I have set right now for the ridge. So it doesn't drive any of the parameters to 0, so we can't really estimate which of these are useful or not, but it is able to get errors down to 0.05 or even lower without too much difficulty. So it seems to do better than the lasso. And it doesn't seem to be overfitting. So again, if you look at this, I mean, these do seem to be converging after 15, 20 size of our training set. We're getting similar performance on the train, the test data here. Right. And if you look at it, except for maybe some of the very extreme ends, so that's a little bit of the cost of not driving things to 0. So we still maybe have some ranges, especially some parts of the range where it's a bit overfitting or a bit wild in what it's doing. But for most of it's clearly much closer of an estimate for most of the time than they had with the lasso there. Oh shoot! I should add in a discussion. So I had 1 or 2 people so far. So if I do ask for a discussion, it's not really an optional thing. Another thing is do use the markdown for your discussions. Okay, so markdowns cell, that's what they're for, and you might want to learn the basics of markdown. Including like creating a table maybe. So, oh shoot, I need to add that in. I thought I had at least the table and a little bit of a discussion here. I'll put that in before I post kind of an example solution here. So I kind of, as I described here, I hopefully I was looking for that you report the underfit, the overfit, the RMSE, and the R-squared score, but also at least 3 different versions of alpha for the lasso and the ridge. Hopefully you were trying to bound your performance, so something that was underfit, something that was overfit, something that was in between, but kind of the best that you could do by doing it by hand. I had a couple of people jump right to doing like a more systematic search here, which was fine, but it's often kind of illustrative to try and do it yourself. So try and find a good setting for alpha by exploring it one by one, and then compare that to what a more systematic search over a range of alpha values can give you. Also, I wanted to mention, so thinking about your class project as well, I should probably formalize this. I'm expecting for your final class project that that you have that you're using IPython notebooks for the majority of the work that you do. And I suppose one IPython notebook might be enough, although you might want to consider, you might want to have separate notebooks where you're doing separate things. Like you might want to do some just initial exploration in one notebook, and you might want to do some feature cleaning, some cleaning or other stuff in another notebook. You might want to have more than one notebook where you explore maybe some different approaches to building a model. So I'm thinking that the project should be big enough that it would benefit from not having everything in just one big monolithic notebook, but breaking it up into a couple of different parts. The other thing is it would be a good idea, if you want me to be able to understand things easier and to be more favorable, more impressed by the stuff, you should use the features of a notebook. So a notebook is meant to be kind of a readable, executable document, right? So it'd be a good idea not to just have code, but to actually give some description of the stuff using Markdown of what you were doing, why you were doing it, what you were thinking at that part, right? So that really helps me a lot to get a feel for what you were thinking as you were doing stuff on your project. If you use, give some English description using Markdown cells of stuff as you're doing it in your notebook. So think of your notebook as a document. So it really should be something that a human is going to be reading, from top to bottom and running from top to bottom with, executable illustrations of stuff in there. I might add in also, I haven't decided yet, but I might ask you to use a README file, which is also uses the same Markdown format as the Markdown cells in Python, or in the Jupyter notebooks. But maybe using like a Markdown file to give me a project kind of report. So I won't make that requirement too big if I do go ahead and ask as a requirement, but something where you have something that's a written document where you give me a introduction, so the normal thing would be an introduction, like a method section, and then like a discussion results sort of section. Right? So I might give you like 3 or 4 different sections where I ask for a paragraph or 2 at least of each one. Maybe a bit more when you talk about your methods and your results of what you did. But yeah, we might just use the top level README for your class project to do that in. Just set that as where it will put your project report basically from your class project. So. Yeah, I guess I got off on that regression though because, right, so it would be useful for this class to learn some of the basics of Markdown. So at least the basics of, how do I create a section or a subsection, how do I get bullet points and number point, maybe create simple tables like you did for this one, and some of the other basic features of Markdown to write up discussions and results and things. So. Okay, and then I'll just mention at the end, I just mostly just checked to see if people did something here, so I probably didn't give a lot of feedback on this. But the point of this was, you know, so if you kind of understood what was being asked for, especially like in 5 and 6, was to do that in a more systematic way. So, you know, scikit-learn, this is only the tip of the iceberg of some of the powerful features that scikit-learn gives you for trying to do this is really useful in, well, a lot of areas, but, you know, definitely when you're getting to try and build your model or compare different models where you're tweaking some metaparameters. So approaching it more systematically using tools like a grid search can be much more productive than just kind of at random or trying to do it by hand and then maybe, you know, keeping like a lab notebook of your results by hand. So a grid search allows you to, in this case, when I post this, if you take a look at it, if you didn't have anything working too well on this, it's not too difficult once you get the hang of it. So basically, you know, you create one of these grid search items. You can pass in just any transformer, including a pipeline transformer like we were using for everything in here. So it just expects that this has the fit transform methods that you can call on it to fit with a set of data. But the tricky part is just this. So I had at least one student asked me about this. You can actually search on the parameters if you're using a pipeline for any part on these if you use the name, you know, if you name the pieces of your pipeline. Right? So here, this is actually 2 underscores. So you have to use whatever part is the metaparameter that you're specifying. So we want to specify a range of alphas that we search on here. So, you know, it's named regression, 2 underscores, and then that particular parameter. So it'll pass in all these 1,000 different alphas. So it'll actually create 1,000 different models using this pipeline with all those different alpha values and compare them and give you the results. So among those 1,000 there, the best one it found for the lasso in this case ended up with a 0.12. So the one I showed by hand was about that. It was about 0.13. Right. So it seems like you can't get it below 0.1. At least I couldn't using the lasso regularization. Right. And yeah, that only pushes it down to about the top 20 features, the top 20 polynomials in this case. So I said you could do it either with lasso or and I don't remember if I said that you should do this. I probably, I wasn't really checking, but so the purpose of this for a single parameter is we want to find out the location that we searched where we ended up with the minimum cost versus alpha. So if we visualize the different alphas that we tried versus the cost that we got for those, what we should see is that some areas of it, alpha is too small, so it's overfitting, which is over half in here, and then other places alpha gets too big, so it's underfitting, so it ends up driving too much to zero here. And then somewhere, if things are hopefully working the way you want, you'll find that you get a minimum of your cost function. So that's kind of what we're trying to search for the alphas here on this assignment. So these are all just, right, so these are just zooming in on there, so it's not continuous, right? So you'll see that there's some weird discontinuities, some jumps in performance that happens here. So, I thought I mean you could have done the same thing using the ridge, right? And probably you would have found that the best you could do would be get an error more like about 0.05 or 0.04, like I was showing by hand above there. So. But you can compare the performance of the best you get with the grid search so in this case the true I guess the point of this final one is that an overpowered model that you're trying to regularize is not going to give you the very best performance possible. So really, if you have some information about what the function is, we can actually get a much better model, an improved model, by getting the exact power correct in this case of the secret function. Right? So if you compare this to, you get a similar thing for the ridge if you optimize your alpha on the ridge. But this one, we're not using any regularization at all. We're simply trying all the powers from 2 to 100 here. Here. But yeah, this code was actually in there, so you could have just, if you had everything working, you should have been able to just uncomment that and try it out. Should have gotten the same results. But you might want to compare the coefficients that are gotten here with the secret function now that you know it. So you'll see that it not only finds the degree that exactly matches what we're going to use for the secret function, but then our final fit. So we're just using a straightforward linear regression here. We're not specifying any regularization or any meta parameters when we create the linear regression for the grid search here. So the only thing that's really being varied is the degree of the polynomial. Okay, yeah, I'll wrap that up. So let me know if there's any questions. I'll post that. I think this is a worthwhile assignment to spend some time afterwards reviewing it. So there's lots of points that were meant to be illustrated on this. So if you didn't catch all those, you might want to. Once I post it, once I get everybody returned, I'll post this somewhere. For the interested student to go back and maybe look at some of these details if you want to. All right, let's see here. Got a little bit more time. I took a little bit more than I was thinking I was going to on that, but there was one more thing on the logistic regression that I thought I would bring up here. Actually, one or two other things. For one, I just wanted to remind people again about the Dr. Ng's lectures. I still think that they're really good lectures, so I had somebody asking about the links. So apparently some of the links that I had on the MyLeo online weren't working, but I think I got them fixed now. But anyway, they're in our class resources. There are some notebooks that that follow his video. So these create, some of these might be useful for you, not only watching the videos, but there's some examples of some Python code for the stuff that he's discussing on there, including there's quite a bit on logistic regression. So this whole his week 3 in this course that he did goes over kind of in a little bit more detail some of the mathematical background of logistic regression. So. One thing when I was rewatching those videos the other day, since somebody was asking about them, I thought I'd just mention real quickly. So we talked a little bit about the decision boundary, and we had some work from our textbook on like a linear decision boundary from the iris data set. So showing what that looked like using the basic logistic regression, how it creates a linear decision boundary. Yeah, if you watch his videos, you know, he'll kind of go through and also discuss a little bit about what a decision boundary is, what it means when you're fitting a logistic regression. But I just thought I would mention that same trick that we were just using for assignment 3, where we were using the same cost function, but we were passing in higher powers of the polynomial to get a nonlinear regression. You can do the same thing with logistic regression to get a nonlinear decision boundary. Right? This is a good thing to understand. This will kind of be the jumping off point for when we start talking about support vector machines and some other stuff. Okay, so in support vector machines, one of the basic innovations for those is they allow you to do a classification and then give an easy way, though, to create nonlinear decision boundaries. But if you understand this, that will be useful when we start talking about that, although that's not until after we get back from spring break where we get into some other more powerful methods than logistic and linear regression. So the basic idea is the same, right? So we could also, the cost function that we modified for logistic regression on Tuesday, where we added in, we put it through the squashing function, so we put it through the sigmoid squashing function last time. That was one of the things that we did, we modified the cost function a little bit. So just to review some of the things, but we modified the cost function a little bit as well. But mathematically, then you end up with a cost function whose derivative is basically almost the same as what we came up with for the linear regression. So that means that you can use exactly the same optimization, like gradient descent, whether you're doing linear regression to fit a line to a set of data, or a logistic regression, which is basically coming up with a decision boundary between a set of points. And like we did for the polynomial regression, you can kind of by hand form a nonlinear decision boundary. Right? So if instead of if we have two parameters, x1 and x2, instead of just using linear combinations as our hypothesis function to fit a linear decision boundary, we could by hand add in some higher degrees, some higher polynomials for our hypothesis function. But then we just have multiple extra theta parameters, but we can do the same optimization then, using something like gradient descent, in order to find the value that minimizes these for a particular set of data that we're trying. The result would be that we would get a nonlinear decision boundary. So like this, if you watch Dr. Ng's this video that where he was talking about these, Here, if you just use only the x squared terms and set the others to 0, you would get like decision boundary, something like that, right? Like a circle, since we have the square of x1 and x2 feature. Right? So something like that would basically give a decision boundary where everything inside would be one class and everything outside the circle would be another class. And I thought I would just mention that because, for a lot of real world data, a simple line is not going to end up giving you a good model that will separate, even for a binary classification task, that will separate the data. So data is often very highly not linearly separable. So, when that's the case, if you want to do well, building a classification model, you're going to have to use something that can create a nonlinear decision boundary. Right? So you can kind of do it by hand, or you can use something like a support vector machine or a tree that does that natively, that will create nonlinear decision boundaries in high dimensions. So, okay, and then finally, since I have just a few more minutes, we actually had, when we first talked about classification in our textbook on the chapter 3, I guess it was, it did talk a little bit about the multi-class classification. I don't remember if I brought it up in class or not, but it was in one of our notebooks. So we were talking about the softmax function, right? So the basic difficulty is that, again, for many types of classification problems, it's not always just going to be a binary classification problem. So often we have the case where we want to predict something where we have multiple classes in the thing that we want to predict. So we have to do something, and some of the methods that we've talked about don't really support that natively. In fact, if you go back and read the textbook here, it implies that logistic regression supports multi-class classification natively. That's true. The reason why it supports it natively, though, is because the softmax function that we talked about allows you to set up a multi-class classification using a single formula. But really, like we touched on Tuesday, there really are multiple, one for each class, even in the softmax. So that's a little bit hidden by the way the softmax is calculated. But so if I have 3 classes like the iris, there really are 3 separate sets of theta parameters that are fit on that. Right? So I don't know if I agree exactly with the way the textbook describes that logistic regression can natively support multi-class classification, because again, even when you're using softmax, some of the stuff in there is really, you're really building a model for each separate class, and then the softmax function combines those into a probability for each that it is for each of the classes. In case I skipped over this last time, when you do another approach, and you can also do this with logistic regression and some of the other methods in the scikit-learn, they might not be able to do a multi-class classification directly, but you can always just train multiple classifiers and then combine them in some ways. So the 2 basic ways that our textbook talks about is the one versus all. So in that case, you build, we did an example of like this before, right? So like for the MNIST train data set, we built a 5 classifier where we had created a data set where all the 5s were true, turned into a binary classification task to detect 5s and not 5s. So if we just had extended that out, so we build a 0 classifier, 0 not 0, 1 not 1, 2 not 2, So you would end up with 10 classifiers on that for for the MNIST data set that has 10 classes. And then basically it becomes a winner take all. So whichever one of the 10, if I'm trying to make a new prediction, I would have to feed that into all 10 of my trained classifiers, and the one that had the highest prediction. So if the 5 had the highest result of the others, we would predict a 5. So you just take the max of those. The other basic approach is 1 versus 1. So here you build, you just pull out the data. So I would pull out all the 1s and the 2s for the MNIST data set and train a classifier to predict whether it's a 1 or a 2. Right? And I have to also the 1 and 3s, the 1 and the 4s, and so on. So if you work that out, that you end up with instead of n separate classifiers. So for 10 classes, I need 10 classifiers for the 1 versus all. For this one, I need actually n squared divided by 2. So you actually need like 150 classifiers if you work it out, because a 1 versus 2 and a 2 versus a 1 is the same. So it's really 10 squared, but half of that approximately. So when you do that, then you have to if you want to make a prediction, you have to feed it into all of the n squared divided by 2 classifiers that you train. And again, though, you're going to figure out which is how do you do. So for that one, it's also kind of a winner take all. So you have to look at which is the yeah, so you have to see which one won the most duels. Yeah, so it's a little bit more complicated to figure out the final decision. So. Anyway, so yeah, we ran out of time. So just to wrap up on that, some of the classifiers in scikit-learn, I mean, you can do multi-class classification, but behind the scenes, since they don't really support it natively, it's really doing that. And you can specify, so if you need to, you can build by hand a 1 versus all or a 1 versus 1 to do a multi-class classification. Or you can just leave it up to scikit-learn to kind of hide the details from that. So like the SGD classifier doesn't do multi-class classification natively. So if you're doing that, so I can't remember the default, if it's 1 versus all or one-on-one. Yeah. So yeah, just going back, if you go back and look at that chapter on the textbook, there was more examples in there, but yeah, you can. Scikit-learn does have things, wrappers basically, so you can more finely control if you needed to. Usually, I've never really done that by hand. I had a case where it seemed like it was useful, but it is useful to know though that behind the scenes that might be happening. So if you're doing a multi-class classification task, it might be useful to know whether your classifier natively supports that, or if it's building multiple classifiers for you and combining the results. All right, yeah, I've got a little bit over, so I'll go ahead and wrap that up there. I'll let you guys go. I'll see you next week. So my next week might be a little bit light, but I plan on doing some review on Tuesday, see if anybody has any questions about the final exam. So that'll be our main thing to concentrate on. All right.